Hello friends. So in our previous lecture we related one of the thermodynamic laws that are associated with enthalpy, not the canonical laws but the Hess's law of heat summation. We related this law to few practical examples. We considered few practical examples that are easily understandable. So one of the example was the formation of water as liquid, and the other example was the corrosion. So we considered these two examples and we saw how Hess's law of summation applies. Now all these Hess's law of summation is permissible because we are able to talk about this Hess's law of summation primarily because we were able to translate the response or the influence of the path variables on a given function, a given thermodynamic function, and this thermodynamic function was internal energy that largely dictated the state of the system, which we used to dictate the state of the system. And when we replaced these path variables or the way of expressing the state of the system using path variables, and when we replaced the path variables with state variables, it allowed us to introduce certain number of intermediate steps that helped us simplify the overall reaction. And when we are able to simplify the overall reaction, then the corresponding changes in the thermodynamic variables where we were able to ascertain it, thereby by relating the corresponding change in the thermodynamic variables with one another and establishing the overall reaction, we were able to understand the change in this particular thermodynamic variable for the overall reaction. So what we essentially did is we first arrived at the understanding of replacing the path variables with state variables, and once we were able to gain that understanding, then we considered rather convoluted or complex reactions. So this convoluted or complex reactions, they might involve just a chemical reaction or a combination of chemical reaction and phase change. Because we were able to translate or replace the path variables dictating the reaction with the state variables, we were able to rather fragment this overall reaction into few different steps. For instance, a straightforward example for us to understand this breakdown or introduction of the intermediate steps is we can observe that while we considered the liquefaction or formation of liquid water. So it involved a chemical reaction and phase transformation, and we considered we broke down this entire reaction into one just involving the chemical reaction and the other involving the phase transformation. So the chemical reaction just gave us H2O in the gaseous state, and the phase change changed this H2O in the gaseous state to liquid. Now when it is our motive to understand the thermodynamic change associated with the enthalpy of the overall reaction, that is we have two gaseous molecules forming a liquid water molecule. Now in that case, since it involves both chemical reaction and phase change, estimating the overall change in the enthalpy becomes quite difficult. However, when we broke that down into smaller fragments, we were able to estimate, or it becomes rather relatively easier to calculate the corresponding change in the thermodynamic variable, which in our case was enthalpy. And because of this introduction of the intermediate step, and because this overall reaction is discussed or described in terms of the state variables, now it becomes possible for us to sum or relate the change in this enthalpy in response to or in accordance with the individual reactions, individual intermediate reactions, and we were able to relate these two enthalpies and ultimately arrive at the overall change in the enthalpy when the two gas molecules of hydrogen and oxygen, when they translate to one liquid molecule of water. So this is what we covered in the previous lecture. So what we essentially did was, whatever theoretical understanding we gained so far, we related to a physical system and we saw how beneficial it is to us. How beneficial it is to us to estimate a thermodynamic change in a complicated reaction when we replace the path variables with state variables. Now again, we ended the previous lecture by stating that the generalized form of Hess's law, it can be expressed in such a manner. The overall change in the enthalpy for any convoluted reaction can be expressed in this manner. So of course whatever manipulations we saw in the previous lecture, so whatever changes, manipulations we make while considering or while recovering the overall reaction, the complex or the convoluted reaction or the fundamental reaction from the intermediate steps. So we need to make some manipulation in order to recover the entire reaction from the intermediate step, and that manipulation needs to be carried over to the corresponding change in the enthalpies, and that's what is represented by this term here or this prefactor here. And when we do that, it can be extended for any number of, so any reaction can be broken down into, any reaction when expressed in terms of the state variables can be broken down into any number of intermediate steps according to our convenience, manipulated in such a way that the overall reaction is recovered, and the corresponding manipulation needs to be extended to the corresponding change in the enthalpies, and by summing it up you will be able to estimate the overall change in the enthalpy associated with the original or the initial reaction. Now in this lecture we will try to understand the enthalpy change that is associated with. So what we have considered is, in the previous lecture we considered the benefits, or one primary benefit of replacing the path variables with state variables, and that helped us arrive at the SS law of heat summation. Now what we will try to do in this lecture is, we will try to understand how this enthalpy change occurs during a phase change. So when considering in the context, when considering the field of thermodynamics in the context of metallurgical engineering, the phase change is one of the principal phenomena that is quite relevant to us. So the phase change, from the point of view of a metallurgist and or a material scientist, the phase change is something that we employ in order to engineer our material, in order to ensure that the material that we work on gives us the desired properties. So in order to achieve that, one of the tools that we have in our hand is to induce certain phase change in the material. Now this phase change is associated with a change, or it is largely governed by, or it can be explained in terms of the change in the thermodynamic functions or thermodynamic variables. Now in this lecture what we will see is how the enthalpy change can be understood, or how the enthalpy change can be studied in relation to the phase change. So in the previous lecture we saw that the overall entire reaction, how complicated it may be broken down into smaller steps, and the overall change in the enthalpy of the entire reaction can be estimated by considering the individual manipulation and the summation of it. Now in this lecture we will consider how this enthalpy change occurs during a phase change. For simplistic consideration, we will assume this phase change to be again freezing, or to be more technical, it is referred to as solidification. So the phase change that we are considering here is freezing or solidification. Freezing is nothing but we have a transition of a liquid to a solid. So this is something that, like we have considered earlier, we observe it in our day-to-day life, or in the technical context, in say a foundry, you will observe this process, or this process is often referred to as solidification. Now let us see how the enthalpy change is associated with this freezing or solidification. Now whenever we discuss the concept of freezing or solidification, we discuss it in relation to a specific temperature below which this particular phase change happens, and that temperature is nothing but the melting point. So the phenomena of solidification or freezing, it is associated with, or it is interlinked with a specific variable or specific temperature, and that is nothing but the melting point below which you have the phase change occurring. Now let us consider water, and this water is now held at a temperature that is slightly close to the melting point. So essentially what you have is, you have a system, and this system comprises of water. Again, for our consideration, for the simplistic understanding, we assume that the system consists of water. And now what you are essentially doing is, you are bringing this system, the entire system, or you are ensuring that you are placing this system in a surrounding that comprises of, or that is maintained at the temperature of Tm, and this temperature Tm is slightly below the melting point. So what essentially you are doing is, you have a system that comprises of water. This is a closed system, closed system meaning you allow the heat to pass through the system, and now essentially what you are doing is you are bringing that system to a surrounding where the temperature of the surrounding is maintained at temperature Tm, which is slightly less than the melting point. So the reason we are considering or talking about in terms of slightly less than the melting point is primarily because the whatever phase change happens, it happens gradually. So that's the reason we are considering a temperature that is just below the melting point, so just below the freezing point. So therefore the phase change that is going to happen, it is easy for us to consider a system, such a system where there is both the solid phase and liquid phase present at the given instant, and this solid phase is growing at the expense of the liquid phase. So that is the reason we are considering, or we are bringing the system to a temperature that is slightly below the melting point. And once we have brought this system to this temperature Tm, we are holding this system at this temperature till the solidification is complete. So what we are essentially doing is we are considering an isothermal phase change. So essentially we have a liquid water, we are bringing it to a temperature Tm, which is just below the freezing point or the melting point, and just when it is below the melting point, what essentially happens is that the liquid starts to solidify or begins to freeze, and when it begins to freeze, since the temperature is just below the melting point, the freezing happens gradually. However, what we are not doing is we are not keep on decreasing the temperature, we are holding the system at this temperature. So therefore what we have is an isothermal system. A system is held at a specific temperature. Now what we have essentially doing in this, what is happening essentially in this system is, so the solid that is appearing in this system, it is stable because the temperature is less than the melting point. The temperature we are holding is less than the melting point, therefore the solid is stable. However, the liquid that is there in the system, it is unstable because again the temperature is less than the melting point, and therefore we have the solid growing at the expense of liquid. Now this, in order for this to happen, what essentially we are doing is we are removing the heat from the solid part of it. So in order to ensure that the solid part of the system is below the melting point at temperature T1, what we need to do is we need to remove the heat out of the solid part, and the heat is sent back to the liquid part. So the heat that is sent to the liquid part ensures that the solid that is formed is at the temperature Tm and it is in the stable condition. So what essentially we are doing is we are removing heat from the system. So by removing the heat from the system, initially this heat is being transferred to the liquid, and finally the heat will be transferred out of the system to surrounding as the solidification reaches the ends. So initially here the heat will be transferred to liquid and this region will be solidified, and the surrounding liquid will be it will have a temperature that is quite high, and as the solidification progresses and once we reach the wall of the system, what we ultimately have is the heat is being transferred to the surrounding. So ultimately the heat is gradually being removed from the system in order to achieve this phase change. So what is happening is the heat is removed from the system, meaning the heat change or the heat transfer is out of the system, so therefore it assumes it is by convention negative. So what is happening is during solidification there is a phase change that is happening. In order to bring about this phase change, the heat is being transferred from the stable phase to the unstable phase, and when this heat transfer reaches the wall, the entire heat transfer moves out of the system to surrounding. So according to convention, when we have such a heat transfer from the system to surrounding, then the heat transfer is negative. Now this heat transfer can be related to the change in the thermodynamic variable associated with the system, and the constant that helps us relate this change or heat transfer to the thermodynamic variable of the system is the specific or rather heat capacity. Now as in most instances, as in the systems that we often come across, often is exposed to a pressure of atmospheric pressure. Let us assume that this system operates at constant pressure. So what we essentially have is this system is operating at constant pressure, like the most systems that we see in our day-to-day life or in our physical surrounding. So in that case, when your system is operating at constant pressure, then the heat capacity, that is Cp, can be the generalized expression for the heat capacity is the change or the heat transfer with respect to the temperature change. So essentially what is happening here is, in order to ensure that the entire system reaches a temperature of T1, what we are doing is we are removing certain temperature of time, we are removing the heat associated with it. Now this is an expression that talks about that relates the heat capacity or the heat capacity to that of the heat transfer associated with the system. Now what we need to understand is, when the pressure is held constant, what we essentially have is this change or the heat transfer along with the work done, which gives us the entire change in the internal energy. So this expression that we have here, when we consider the pressure to be constant, what happens is that we can bring this over here, and ultimately we saw that this change or heat or the transfer of heat can be related to the corresponding change in the enthalpy, or rather the corresponding change in the enthalpy when you take or consider just the heat transfer on one side and bring about all the other variables on the other side from the first law of thermodynamics. So what essentially we have considered is, we have considered a phase transformation at constant pressure, and during this phase transformation the heat is removed from the system, and because the heat is removed from the system, we have to, by convention, the heat transfer is negative, and since the pressure is constant, from the first law of thermodynamics we can state that the heat change or the heat transfer brings about a corresponding change in the enthalpy, and now we can relate this corresponding change in the enthalpy to this heat capacity. However, we need here to understand that since we are considering a isothermal phase transformation, this relation cannot be used directly because dt here becomes 0. So the reason we brought about this heat capacity, even though the heat capacity helps us understand or relate the enthalpy to the heat transfer and to the constant, a material constant, in case of isothermal transformation it cannot be directly employed because dt in case of isothermal transformation is 0, and therefore this entire term becomes infinity in case of isothermal phase change. So therefore what we need to do is, we need to, for isothermal reactions alone, in order to understand the phase change, we need to stick with this expression, that is the heat change is directly related to the corresponding change in the enthalpy. So in case of isothermal reaction, because the dt is 0 and the entire expression of the heat capacity becomes rather ill-defined, so we need to stick with this reaction or with this expression here that comes from the first law of thermodynamics. So in this case we need to understand that during the isothermal process, in order to relate the heat capacity to that of a change in the thermodynamic variable, we cannot, or rather in order to relate the heat transfer to that of a change in the thermodynamic variable, we cannot go to the expression of heat capacity, but we have to stick with the first law of thermodynamics. And this gives us the expression here, primarily because we have assumed the pressure to be constant. Now we saw that according to our convention, for this isothermal phase change the heat transfer is negative. So that means delta H, the corresponding change in the enthalpy, is negative. So what we essentially have is, we have an isothermal phase change, and the corresponding change that occurs in this isothermal temperature or corresponding change in enthalpy that occurs in this isothermal temperature. is negative. So if we assume that this delta H, it comprises of two components, that is enthalpy of the liquid at temperature Tm and the enthalpy of solid at temperature Tm, then the delta H will be the difference between the enthalpy at the final product, enthalpy of the final product minus the enthalpy of the initial product. So that means final product here is the solid and the initial product here is the liquid. Both again are operating at the same temperature, and we saw because of the heat is being removed from the system, by convention the delta Q is negative, and therefore since delta Q is nothing but the change in the enthalpy, it is also negative. So that means this relation or this difference between the enthalpy associated with the solid minus the enthalpy associated with the liquid at the temperature just below the melting point is less than 0, or meaning negative. Now when we bring this term to the other side, what we have is during the phase change, that is the solidification here, the enthalpy of the solid is less than the enthalpy of the liquid. So we arrive at this relation between the two enthalpies during an isothermal transformation. What we essentially have is, during an isothermal phase change particularly, what we essentially have is the enthalpy of the product is less than the enthalpy of the initial reactant. So here the enthalpy of the solid is less than the, so enthalpy of the ice here is less than the enthalpy of the our initial reactant or the initial state, that is enthalpy of liquid water. Now the reason we stuck with this reaction, that is, or with this relation, that is the heat change or the heat transfer is equivalent to the change in the enthalpy, is because of we assumed an isothermal transformation, and therefore we were not allowed to use the heat capacity relation. Now let us assume that instead of bringing your system down just below the melting point, let us assume that the system is brought well below the melting point. So from Tm we are bringing the system to well below the melting point, say T0. So if we assume our melting point of ice or the melting point of water is 0 degrees Celsius, now initially we bring it to say -1 degree Celsius, and now just to give you an example, so initially we bring it to -1 degree Celsius, and now we bring it to say -10 degrees Celsius. Now what essentially we are doing is we are changing the temperature now. So there is a definite delta T that is involved. So initially we considered isothermal phase change. Now we are bringing down the temperature from T1 to T0. Now in that case we have a definite delta T. So delta T is not equal to 0 when we bring the temperature from T1 to T0. However, we need to know that the Tm is greater than T0. We are lowering the temperature. Now in this case, so what we have is, once we bring the temperature down, we have a corresponding change in the enthalpies as well. So initially we had a system at Tm. So we had a system at temperature Tm. So we had a corresponding enthalpy for the solid at Tm and a corresponding enthalpy for liquid at Tm. Now we are bringing this system to a temperature T0. Now we will have a corresponding enthalpy for solid at T0 and a corresponding enthalpy for liquid at T0. Now these two are known to us. So we have considered these two in the previous expression. We have related it to the heat transfer, and we have seen that one is lower than the other. Now using these two, let us try to find out the enthalpy of the liquid and solid at the new temperature T0. So now we need to find these two variables or express these two variables in terms of these other two enthalpies that we used in our previous instance. Now in order to do that, let us consider the heat capacity. Now that the change in the temperature is not equal to 0, we can go for the expression of heat capacity at constant pressure, which is nothing but delta Q at constant pressure by Tt. Now at constant pressure, we have already seen that the heat transfer is equivalent to the change in the enthalpy. So that means the Cp is nothing but delta H, again because of the constant pressure, delta T. Now we can use this expression here because now we are considering a non-isothermal change in state. Whenever we have an isothermal change in state, we cannot use this expression because delta dt becomes 0 then. However, when we are considering a non-isothermal change in the state of the system, then we are allowed to use this expression here. Now what essentially can be done here is, so we have now an expression for Cp that relates the change in the enthalpy to the change in the temperature. And now what can be done is, we can rearrange this expression in such a way that delta H is nothing but the product of the heat capacity at constant pressure and the temperature change. Now essentially what we have to consider is, first we need to consider the enthalpy change for liquids. So when we consider the enthalpy change for liquids, we have enthalpy of liquid at the final state T0 minus enthalpy of the liquid at the initial state Tm. So we are bringing the system from T1, Tm to T0. So the final state is T0 and the initial state is Tm. So the liquid, it remains the same. So we are considering the enthalpy of liquid at T0 minus enthalpy of the liquid at Tm. This is equal to nothing but the corresponding heat capacity of the liquid, so Cpl minus, or and the product of, again the final temperature is T0 and the initial temperature is Tm. Now again we can rearrange this in such a way that the enthalpy of liquid at T0 is equal to enthalpy of liquid at Tm plus the corresponding heat capacity of the liquid T0 and the product of T0 minus Tm. So this is one way of, or this by using these variables here, now we are able to estimate the enthalpy of liquid at the new temperature. So you have a system, you are bringing it to a lower temperature from T1, Tm, you are bringing it to a lower temperature T0, and you are holding the system at T0 for a prolonged period of time so that the phase change happens. So essentially you are bringing the system to T0 and allowing the system to solidify at T0. So instead of allowing the system to solidify at Tm, in this case you are allowing the system to solidify at T0. So essentially at T0 still what you have is the isothermal phase change is happening. However, now it occurs at a lower temperature. So in order to understand, in order to arrive at similar expression like what we have here, in order to arrive at similar relation and understand the enthalpy of solid at T0 and enthalpy of liquid at T0, in order to know that, we begin with the consideration of enthalpy of liquid at the Tm and similarly enthalpy of solid at Tm. So if you consider the same expression here for solids, you will end up with similar reaction, similar relation, that is enthalpy of solid at T0 is the summation of enthalpies of solid at the initial state plus the respective heat capacity and the corresponding change in the temperature. So now what we are essentially considering is, we are considering a change in the state of the system at T0. So like Tm, we are considering a change in the state of the system at T0. So what essentially is happening is, the heat is again being removed from the system. So therefore what is even at T0, the delta Q is negative, and that means delta H is also negative. Again, this is not at Tm but at T0. And similarly, if you consider this relation here, what you would end up having is H is T0 minus H L T0 is what we would like to see. So we would like to understand the change in the enthalpy, and this is negative. Now since we already have an expression for Hs T0 and HL T0 in terms of the corresponding enthalpies at the temperature that is close to the melting point, we can try to express this in a different manner. So therefore this difference in the enthalpy of solid and enthalpy of liquid at this lower temperature, that is T0, which is much lower than Tm, can be expressed as is nothing but H is minus HL, both at the higher temperature Tm. So what we are essentially doing is we are subtracting these two, and then we have CPS minus CPL and T0 minus Tm. So this is what we have, or this is the difference between, or the difference in the enthalpy of solids and the enthalpy of liquid at the new temperature, or at the temperature that is much lower than Tm, and we are expressing these two in terms of this relation here. So essentially we have subtracted these two, and therefore we have Hs minus HL, and this here is positive, therefore this here is positive. Now we have considered two temperatures, Tm, a phase change in Tm, and a phase change in T0. The phase change in T0 is rather characterized by this difference in the enthalpy, and the phase change in Tm is characterized by this difference in the enthalpy. So if you could recollect, initially we arrived at this expression. So this expression here, it is nothing but the difference in the enthalpy when the phase change is occurring at Tm, and this expression here is nothing but the change in the enthalpy when the phase change occurs at T0. So this expression here, that the one in green, is nothing but delta T, change in the enthalpy at temperature T0, and this expression here is nothing but change in enthalpy at temperature Tm. Now we have an additional term, that is Cp, or rather CPS minus CPL. So the heat capacity of solid minus heat capacity of the liquid, and T0 minus Tm. So what we have essentially done is, we have essentially related phase change at two different temperature in this equation. So in the left hand side of the equation, what we have is the enthalpy change that occurs when the phase changes at a lower temperature, and in the red we have the enthalpy change that occurs when the phase change at a temperature that is close to the melting point. So we are relating the enthalpy change at two different temperature, on the left hand side a lower temperature, on the right hand side a quite higher temperature, and the way these are related is through these terms here. So these are equal, plus there are these two terms associated with it. Now this is a negative term, this term here is a negative term, and this term here is a negative term. Both are negative terms because of this relation here, because primarily what we have is the phase change is governed by removal of heat. So therefore what we have is, here this term is a negative term and this term is a negative term. If this term is negative, the additional term is negative, then what we essentially have is this difference in the enthalpy is greater than that of this difference in the enthalpy. So let me repeat, you have two negative terms here and here, and if this difference is negative, we can get rid of all the negatives, and if we get rid of all the negatives, then essentially this change in the enthalpy is summation of the change in the enthalpies at higher temperature plus some other term. Let me repeat, this enthalpy is negative, this enthalpy is negative. Now there is this additional term, and if this additional term is negative, we can get rid of, if this additional term is negative, we can get rid of all these negatives. So we can get rid of all these, we can remove, because we have talking in terms of an equation, we can get rid of all these negatives, and the only way we will be able to arrive at the change in the enthalpy at lower temperature is adding a certain term to the enthalpy change at higher temperature. So therefore it means that the enthalpy change at lower temperature is greater than the enthalpy change at higher temperature. So what essentially we have is, if this term is negative, we can get rid of all the negative terms and we will be dealing with just the positive terms, and this term, then when we consider just the positive terms associated with enthalpies and this additional term here, now in order for this enthalpy at higher temperature to be equal to the enthalpy at lower temperature, we need to add some other terms to it. So that means enthalpy at lower temperature is greater than the enthalpy at higher temperature. So that is what we see when we reduce the temperature from T1, Tm to T0. Now, the way this can be negative is only when either of these terms are negative. If both of these terms are negative, then this becomes positive. Then we will not be able to arrive at that conclusion that this term, that is the enthalpy change at lower temperature, is greater than the enthalpy change at higher temperature. So in order for us to have that this overall term, these two terms, the product of these two terms is negative, one of these terms need to be negative, and we have already seen that T0 is less than Tm. So therefore this term is negative. And this term needs to be positive. Primary, or this term can be understood, or conceptually it can be observed that this term will be positive because the description of this Cp here is this, or the description of the Cp here in a generalized way is this. The change in the temperature, or the ratio of the heat exchange and the corresponding change in the temperature. Now when you compare the heat exchange and corresponding change in the temperature, the heat exchange, what it essentially brings about, again for a conceptual understanding, the heat exchange, what it brings about is, supposing you are supplying heat to a system, what it brings about, it increases the kinetic energy of the entities or atoms associated with the system, and that correspondingly translates to temperature. Now since in solids the atoms have specific position and the kinetic energy of the atoms depend on the vibration, there is not much room for the atoms to vibrate in solids. So therefore the temperature increase for a specific or a constant heat exchange in solid is much lower than in case of liquids. Let me repeat, the primary difference between solids and liquid is that in solids you have the atoms occupy a specific position. Now when you supply heat to solid, the temperature needs to increase. The temperature increase means the kinetic energy of these atoms have increased, meaning the atoms are vibrating at a greater phase. Now since the atoms are locked in solid, the amount of vibration you see in solid is much restricted than liquid. So therefore the dt here will be much lower in solids. This dt here will be lower in solids when compared to liquids. So therefore what we have is, since the denominator is lower in case of solids, what we essentially would have is, let me use a different color. So what we would essentially have is, since the denominator is lower for solid, then the Cps would be greater than Cpl. So when you have this relation, then this term becomes positive. So this term becomes positive and the adjacent term, the other term becomes negative. So ultimately the entire term is negative. So what we have ultimately is, what we have arrived at is the delta H, the change in the enthalpy at lower temperature, is equal to the change in the enthalpy at higher temperature plus the difference, the difference in the corresponding heat capacity and the temperature change. So this term is negative, this term is negative, and this term is negative. So the negative, all the negatives can be removed and made it to positive, and this relation shows that delta H at T0 is greater than the delta H at Tm. So if we graphically represent whatever we have considered so far, it would look something like this. So let us consider the x-axis to be the temperature. So this is the temperature, and the y-axis to be the enthalpy. And now we are considering a temperature that is T0, which is here, or rather Tm, which is here. And initially we saw that at this temperature Tm, the enthalpy of solid and the enthalpy of liquid, the difference between these two is less than 0. So therefore the enthalpy of solid is less than the enthalpy of liquid. So what we have is at Tm, this would be the enthalpy of liquid because of this relation here, and this would be the enthalpy of solid. And at Tm, during the phase change, this would be the difference in the enthalpies. Now what we are doing is we are considering a change in temperature. So we are moving to a new temperature, that is T0, and this T0 is less than Tm. And we saw that there is a way for us to relate the Tn and or the corresponding enthalpy of the liquid at T0 to the enthalpy of liquid at the higher temperature Tm. So we arrived at an expression for that. And when we compared the change in the enthalpies between the liquid and solid at lower temperature, we saw in our previous relation, this relation shows that at lower temperature the change in the enthalpies will be higher when compared to the higher temperature Tm. So therefore it will be higher. So rather, so this would be our enthalpy of solid at T0. So what we have is, we have a significant difference or significant change in the enthalpy at lower temperature and not so significant change in enthalpy at higher temperature. And we have already considered that we have moving the system from Tm to T0, and that helped us introduce the constant Cp. So this non-isothermal change in the temperature helped us introduce the Cp and relate HL, that is enthalpy at Tm of liquid at temperature, higher temperature, to the enthalpy of liquid at lower temperature we related these to the material constant here. So this is how the graphical representation of all the insights we have gained looks like. And if we consider that it is the difference in the enthalpy, it is the lower enthalpy, or the system wants to get to the lower enthalpy, and if it's the difference in the enthalpy that brings about the phase change, or the phase change can be, the driving force of the phase change can be discussed in terms of the difference in the enthalpy, then we observe that at lower temperature the solidification is governed by a greater driving force when compared to the higher temperature. So in case of an isothermal transformation, at lower temperature the difference in the enthalpies are quite significant when compared to the higher temperature, the temperature that is close to the melting point. So therefore correspondingly the driving force, the force that we want, or the force that governs the phase change, is quite higher at the lower temperature when compared to that of the higher temperature. So what essentially we have done in this entire lecture is that we have considered isothermal phase change at two different temperatures. So initially we considered the isothermal phase change at temperature Tm, that is close to the melting point. And when we consider this isothermal phase change, we saw in case of isothermal phase changes we cannot use this constant. However, we can use the first law of thermodynamics, and here since the heat is being removed out of the system, we understood that the enthalpy of solid is less than enthalpy of liquid. So in case of solidification, the enthalpy of solid is less than the enthalpy of liquid because this heat is being removed. So that is the first conclusion that we arrived at. Now once we arrived at that particular conclusion, we reduced the temperature. We brought the system to a new temperature, a further lower temperature. Now this system again is liquid, and we are considering this entire liquid at a lower temperature, and now we are allowing the phase change to happen. So we are bringing a system comprising of liquid to a lower temperature, that is T0, and allowing the phase change to occur. Now this enthalpy of the system at this new temperature, that is T0, can be calculated or estimated from the original enthalpy as T1, Tm, because now the dT is not zero. Now essentially, since we are changing the temperature, dT is not 0. So therefore we introduce, by using the constant, that is the heat capacity, we were able to ascertain the enthalpy at lower temperature from the enthalpy at higher temperature and this heat capacity here, and correspondingly we were able to also identify the enthalpy of the solid at lower temperature from its corresponding enthalpy at higher temperature. So once we were able to do that, we considered the difference in the enthalpies. Here we consider the difference in these two enthalpies rather, and we found out that when we consider the difference in these two enthalpies and compare it with these two difference in these enthalpies like we done here, we saw that theoretically this difference in the enthalpy is quite higher when compared to the difference in the enthalpy at higher temperature. And this is primarily because we have an additional term here, and this additional term is what quantifies how with decrease in temperature this difference increases. So as you decrease the temperature, below the melting point, the enthalpy change associated with solids and liquids also, this difference, it increases. The more you decrease the temperature, the more the difference between the enthalpies of solid and liquid, it increases, and that is what is being captured in this graphical representation here. So essentially, if we translate this enthalpy change as the driving force for solidification, then for isothermal solidification, this difference in the enthalpy, since it becomes greater as you reduce the temperature, the driving force for solidification increases. So what essentially we have done in this lecture or in this theoretical consideration is, we have shown that the rate at which, or the driving force for solidification at 0 degrees Celsius, like we considered in few slides before, at 0 degrees Celsius will be higher when you consider the driving force for solidification or freezing at minus 10 degrees Celsius. So that is what the understanding we gain using this difference in the enthalpies. So with this, we will wind this lecture up, or we will wind this module up. We have considered the basics of basic terminology associated with thermodynamics, and we have considered the first law of thermodynamics, and now the first law of thermodynamics has helped us understand how with the change in the temperature, the driving force for a given phase change for an isothermal phase changes. So we have considered two isothermal phase changes, and we saw that particularly the phase change here is solidification, and we saw that with change in the temperature the corresponding driving force changes, and this driving force here is being expressed in terms of the enthalpies. So beginning with the first law of thermodynamics, just by considering the first law of thermodynamics, we are now able to say that when for solidification, when we reduce the temperature, or particularly when we are considering the isothermal solidification, when we reduce the temperature or when we hold our system to a lower temperature, the driving force for solidification is higher when we hold the system at higher temperature. So with this, we are winding up a module, and from the next lecture onwards we will be moving on to a next module. Goodbye.